How did a living, breathing creature manage to reach a terminal velocity of 390 kilometers per hour, clocking in faster than a Formula One car and even outstripping the legendary fighter jets of World War II? All without the help of a single jet engine or an ounce of rocket fuel. It seems like a physical impossibility. At that speed, the sheer force of the wind should rip through lung tissue like wet paper. The massive G-force alone should be enough to cause a total blackout, shattering internal structures and plunging the eyes into absolute darkness. Yet, this bio-machine doesn't just survive, it thrives in the chaos. More details on this lethal engineering all in the video ahead. We are looking at the Peregrine Falcon, but for the next few minutes, forget everything you know about birds. This isn't just an animal, it is a living, breathing missile. A biological projectile forged through millions of years of evolutionary refinement to carry out the perfect airborne assassination. Its mission is simple: to identify, track, and eliminate its target with a level of precision that would make modern stealth fighter pilots envious. This is Mother Nature's ultimate strike package, a masterpiece of biological engineering designed for a high-speed, targeted kill. But the real question is, how does it manage to survive the extreme physics of the dive? Since the hunt begins miles above the Earth, the descent requires more than just gravity. It requires a level of tactical planning and structural integrity that defies basic biology. So, how does it handle the pressure? And why doesn't it explode on impact? Let's examine the strategy behind this natural-born killer. To pull off an operation of this magnitude, the mission begins with high-altitude reconnaissance. The Peregrine doesn't just fly, it patrols the upper atmosphere, often reaching heights of over 3,500 feet. This isn't just about gaining a bird's-eye view, it's about weaponizing potential energy. By climbing to these extreme altitudes, the Falcon is essentially storing the energy it will later convert into pure, unadulterated speed. But there's a deeper tactical layer to this positioning. To remain undetected, the Falcon utilizes the sun's blind spot. By keeping the sun directly behind it, the glare masks its silhouette from the prey below. It is essentially utilizing biological stealth technology, ensuring the target never realizes the threat exists until the window for escape has already closed. Next is target acquisition. How does it manage to lock on to a moving target from such a massive distance? The answer lies in the Peregrine's vision, which is arguably the most advanced optical system in the natural world. It can pinpoint a pigeon or a duck from more than 3 kilometers away. To put that into perspective, its eyes function similarly to the phased array radar found on a modern F-22 Raptor. It isn't just seeing shapes, it's processing real-time telemetry. The bird's retina is packed with millions of light-sensing cells, and its dual-purpose fovea acts like a specialized lens system. This allows the Falcon to maintain a razor-sharp focus on the target while simultaneously navigating the complex, high-velocity air currents of the upper atmosphere. Once the lock is confirmed and the trajectory is calculated, the transition from scout to projectile begins. The moment the dive begins, known as the stoop, is where the real engineering magic happens. This isn't a simple fall, it's a controlled, high-speed ballistic entry. To minimize aerodynamic drag, the Falcon undergoes a radical physical transformation. It rucks its shoulders and tucks its wings tightly against its torso, assuming a perfect teardrop shape. In the world of fluid dynamics, the teardrop is the most efficient form for slicing through air with minimal resistance. By reducing its cross-sectional area, the Falcon eliminates nearly all parasitic drag. Its feathers, which are usually soft for standard flight, are compressed into a rigid, armor-like shell to withstand the sheer force of the oncoming wind. Every single anatomical detail is now optimized for one thing: the acceleration curve. Let's look at the numbers. Gravity alone isn't enough to reach the speeds we are talking about. To break the 300 km/h barrier, the Falcon actually pumps its wings during the initial phase of the dive to overcome air resistance and kickstart its momentum. We are seeing an acceleration from a cruising speed of 60 km/h to over 320 km/h in a matter of seconds. The sheer kinetic energy being generated is staggering. As it nears the terminal phase of the hunt, the Falcon is moving so fast that the air itself begins to behave like a solid wall. Yet, the bird maintains absolute stability. Its tail acts as a precision stabilizer, making micro-adjustments to the trajectory at millisecond intervals. It's a level of flight control that even the most advanced fly-by-wire systems struggle to replicate. At this stage, the Peregrine is no longer an animal. It is a precision-guided munition traveling at the absolute edge of biological limits. But this brings us to a critical technical challenge. When you are traveling at nearly 400 km/h, the margins for error completely disappear. A single miscalculation doesn't just mean a missed meal, it means a catastrophic collision. So, when the impact finally occurs, what exactly happens? Does the Falcon simply crash into its prey? Or is there a more sophisticated strike mechanism at play? And more importantly, how does it ensure a successful kill without destroying its own skeletal structure in the process? The answer lies in the different engagement scenarios. If the Falcon hits a target at 390 kilometers per hour, shouldn't it shatter its own skeletal structure? Think about it. A direct head-on collision at that velocity is equivalent to a high-speed vehicle crashing into a concrete barrier. From a purely mechanical standpoint, the Falcon's bones shouldn't be able to withstand that kind of instantaneous deceleration. So, how does it deliver a lethal blow without committing biological suicide? To understand the answer, we have to look at the attack strategy through 3 distinct tactical scenarios. Let's examine Scenario 1, the kinetic missile. This is the Falcon's primary method for high-velocity engagements. Instead of extending its talons to grab the prey, which would risk breaking its legs upon impact, the Falcon clenches its feet into a tight ball, essentially creating a living knuckle. At 350 plus kilometers per hour, the Falcon doesn't need to pierce the skin to be lethal. It relies entirely on the transfer of kinetic energy. By striking the head or the spine of the target, the impact delivers hundreds of pounds of force per square inch. This instantly snaps the vertebrae or causes a massive internal concussion. It is the biological equivalent of an unguided bunker buster bomb, using pure mass and extreme velocity to annihilate a target through blunt force trauma. In this scenario, the prey is literally dead before the sound of the Falcon's approach even reaches its ears. But what if the mission requires a more surgical touch? Let's consider Scenario 2. This is what we call the surgical slice. In situations where the Falcon is diving from a lower altitude or at a slightly reduced speed, it may choose a more refined engagement. As it closes in, it extends its rear talon, known as the hallux claw. This claw is razor-sharp and specifically designed for high-speed lacerations. Instead of a direct smash, the Falcon delivers a raking blow as it passes. The hallux acts like a scalpel designed to sever the primary flight tendons or slice through the carotid artery in the neck. This is a precision strike intended to disable the target's ability to fly, allowing gravity to do the rest. The efficiency is chilling. The Falcon minimizes its own risk of injury while ensuring the target is neutralized in a single high-speed pass. Finally, we have Scenario 3, which is the most technically demanding. This is the high-G dogfight. What happens if the prey detects the incoming strike and begins a series of desperate, evasive maneuvers? This isn't a simple dive anymore, it's a high-stakes aerial engagement. To maintain its target lock, the Falcon has to execute turns so sharp they generate up to 25 Gs of force. For a human perspective, the most elite fighter pilots, even with advanced G suits, will experience a total blackout at around 9 or 10 Gs. The Peregrine is pulling nearly triple that limit. It uses its entire body surface, adjusting the angle of its wings and the orientation of its tail at millisecond intervals to stay on course. This allows the Falcon to shadow the target's every move, closing the distance until the window for a strike opens. The ability to endure these forces is what truly separates the Peregrine from every other predator on the planet. But this raises a profound engineering question. How does a creature made of organic tissue survive 25 Gs? Why don't its lungs collapse under the pressure of the wind? And how do its eyes remain functional during such extreme acceleration? This leads us to the heart of the mystery. To find the answer, we have to look inside the machine. We need to dissect the anatomical engineering that makes this 390 km/h dive possible. To understand how this biological weapon operates at the absolute edge of physical possibility, we need to strip away the feathers and analyze the underlying hardware. This isn't just a bird, it is a masterclass in high-speed fluid dynamics and structural engineering. When we look at the Peregrine Falcon through a micro view, we discover that every single component is an evolutionary answer to a lethal engineering problem. We've broken this down into 3 primary technical systems that allow the Falcon to survive the physics of a 390 km/h dive. Let's start with Step 1, the intake system. In the world of aviation, managing air pressure is the difference between a functioning engine and a catastrophic explosion. For a Falcon traveling at terminal velocity, the air itself becomes a weapon. If a Peregrine were to simply open its mouth or nostrils to breathe during a stoop, the sheer force of the ram air pressure would be enough to rupture its lung tissue instantly. Think of it like this: if you stick your head out of a car window at 60 miles per hour, breathing becomes difficult. Now, imagine quadrupling that speed. The air would be forced into the lungs with such violence that the internal structures would essentially detonate. So, how does the Falcon solve this? The answer lies in a specialized anatomical feature called tubercles. Inside the Falcon's nostrils, there are small, bony, cone-shaped structures located at the center of the opening. These act exactly like the inlet cones found on supersonic jet engines, such as the SR-71 Blackbird or the MiG-21. As the high-velocity air hits these tubercles, it creates a controlled shockwave that breaks up the direct force of the wind. This turbulence slows the air down and regulates the flow before it enters the respiratory tract. It is a piece of high-precision fluid engineering that allows the bird to breathe comfortably while traveling faster than a falling stone. Without these biological intake cones, the Falcon's high-speed mission would end in a respiratory blowout before it even reached the target. Step 2 involves the optical system. When you are traveling at 240 miles per hour, the environment becomes incredibly hostile to organic tissue. At these speeds, the wind acts like a sandblaster, and even a tiny speck of dust could cause permanent blindness upon impact. Furthermore, the sheer force of the air would dry out a standard eye in a matter of seconds. To counter this, the Peregrine utilizes a specialized piece of hardware known as the nictitating membrane. This is a semi-transparent third eyelid that slides horizontally across the eye. It functions as a set of high-performance aerodynamic goggles. The membrane is clear enough for the Falcon to maintain its target lock while providing a physical barrier against debris and wind blast. It also secretes a highly viscous fluid that acts like a biological lubricant, ensuring the eye remains moist and functional under extreme aerodynamic stress. But the engineering of the eye goes even deeper. To maintain its precision-guided trajectory, the Falcon needs a level of visual processing that far exceeds human capability. The Peregrine's retina contains two distinct foveae, or focal points, in each eye. This dual fovea system allows the Falcon to have a simultaneous wide-angle view and a highly magnified, telephoto-style zoom on its target. It is essentially a biological version of a dual-sensor camera rig found on advanced reconnaissance drones. This allows the bird to track the target's every micro-movement while simultaneously monitoring the surrounding airspace for obstacles or threats. This optical telemetry is processed at a rate that allows for millisecond corrections to its flight path, ensuring that the target remains locked in the center of its crosshairs throughout the entire descent. Finally, we have Step 3, the variable sweep wing system. During the terminal phase of the dive, the Falcon has to manage a massive amount of kinetic energy. It needs to be able to make sharp, high G-turns or pull out of a dive without experiencing a stall, a condition where the air no longer flows smoothly over the wing, causing a total loss of lift and control. To solve this, the Falcon utilizes a specialized set of feathers called the alula. The alula is a small, thumb-like projection located on the leading edge of the wing. In a standard flight configuration, these feathers remain flat. However, during high-angle maneuvers or sudden braking, the Falcon can pop the alula feathers upward. This creates a small gap that redirects a high-velocity stream of air over the top surface of the wing. In aeronautical engineering, this is known as a leading edge slap. It prevents the airflow from detaching, allowing the bird to maintain absolute control at angles of attack that would cause a modern fighter jet to fall out of the sky. This biological air brake and stabilizer system is what gives the Falcon its unmatched maneuverability. It allows the bird to transition from a 390 km/h projectile to a precision striker in a heartbeat. When you combine these three systems, the intake cones, the protected dual-sensor optics, and the variable sweep stabilizers, you realize that the Peregrine Falcon is a masterfully engineered machine. Every bone, every feather, and every sensory organ has been optimized to overcome the crushing laws of physics. It is a total integration of hardware and software, designed for one specific, lethal purpose. This level of engineering is why the Peregrine remains the undisputed king of the skies. It took humanity nearly a century of wind, tunnel testing, and supercomputer simulations to achieve the flight efficiencies that this creature was born with. It proves that when it comes to high-stakes, high-speed operations, the most advanced technology on the planet isn't made of titanium or carbon fiber. It's made of bone and muscle. But there is a final lesson we can learn from this biological assassin. The evolution of flight isn't just about speed, it's about the relentless pursuit of perfection in the face of impossible odds. It serves as a reminder that nature is, and always will be, the ultimate engineer. If you found this breakdown of biological engineering fascinating, there is plenty more original content where this came from. We specialize in mashing up the worlds of engineering and nature to show you how the world really works. It took humanity nearly a century of wind, tunnel testing, and supercomputer simulations to achieve the flight efficiencies that this creature was born with. It proves that when it comes to high-stakes, high-velocity operations, the most advanced technology on the planet isn't always made of titanium or carbon fiber. Sometimes it's made of bone and muscle. But there is a final lesson we can learn from this biological assassin. The evolution of flight isn't just about speed, it's about the relentless pursuit of perfection in the face of impossible physical odds. It serves as a reminder that nature is, and always will be, the ultimate engineer. If you found this breakdown of biological engineering fascinating, there's plenty more original content where this came from. We specialize in deep dives into the machines, both man-made and natural, that define our world. Please consider subscribing and hitting that notification bell so you never miss a video.